Thank you, Sune, for the invitation and organizing this workshop. And thank you, him, for having us all here. So I will give this introductory talk, trying to say a few words about what is fusion system, what is it good for, how can we use it in the real world. So I'll start with let P be a prime number, and S a finite P group, having two subgroups, P and Q. And let's take an element in S giving a conjugation from P to Q. So let's say that Q is the conjugate of P with respect to U, meaning in group theory terminology, all the conjugates by U in that. So this is what we call conjugation in S, right? By elements in S. And how do we capture that? If we want all the elements giving this conjugation, we have the transporter in S, namely the normalizer, so the transporter from P to Q, all those elements in S giving the conjugation from P into Q, right? And if you want to see all S conjugations, what you do, you take this transporter and you quotient out all the conjugations that are trivial on P. This is the centralizer on S in P, and we'll give it a notation because we'll use it later. So we say that those are the homomorphisms from P into Q given by conjugation by S. Just to introduce some terminology because it will be used all over this conference. When P is Q, then this is just the automorphisms of P given by conjugation by S, right? And what we have here, it's instead of transporter, we have what's called the normalizer in S of P. Okay, so this is the picture given by S on two of its subgroups. What about a slightly more general picture? Take G a finite group. Take S as before with P and Q subgroups of S, and take a G inside of this finite group and consider the conjugation by this element G. So this is again the conjugate of P by G, and we have the same things, but just to make a difference from the fact that the action happens, the conjugation happens, conjugation action happens inside of S, but is given by something else. We say that this is fusion in S given by G. Okay, so that's just, you have to think this fusion is something inside of S between subgroups given by an entity that's above, that's somehow exterior to this subgroup. And if you want the conjugation that you had before, it's just the trivial fusion that always come when you have this one. So again, you'll have the transporter NG PQ. You'll have the homomorphisms, the morphisms by conjugation given by G between P and Q with the same notations. as before. So you want to capture this information. You want to capture this information. You would put it in a axiomatize this. So you get the fusion system F on some P group S, which is a category that has objects, simply the subgroups of S, and homomorphisms would be those homomorphisms between two subgroups of S that contain the homomorphisms by conjugations with S, and are all injective group homomorphism. What we ask more is that once you have a morphism from P to Q in the fusion system, then you want that it factors through an isomorphism. So this is phi restricted to P. So this is isomorphism in F, meaning that the other map, the map going from phi of P to P, is also a morphism in the fusion system. And the inclusions are anyway contained because here you have the trivial element that will give you trivial fusion. So this is the fusion system, and if you want to come here and construct the one that's given by the fusion in G, you just have you note it by FSG, so the fusion system on S given by G. Okay, just to introduce some notation. The problem here is that we are somehow in a dry land. There's very few things that you can do with this setting. So you need some more, some more properties in order to do something meaningful with this theory. So what you would put as an extra condition is that S is a CeLO. So you look at the situation where S is a CeLO P subgroup in G. What you have more, you have CeLO theorems, and this is already huge with respect to what you have in the first setting. So what is the corresponding situation in fusion system? Will be saying that F, the fusion system that you constructed before, is saturated if you have two things. First of all, you want to capture not only the fact that S is somehow maximal, so how you write that? You say that the inner automorphisms of S are a CeLO P subgroup of the automorphisms in F of S. Now I realize that I didn't write here that when P is Q, then the notation of this would be the automorphism F of P, right? So this is the maximality condition on S, and the other one would be some kind of an extension condition. So if a subgroup of S is what we call fully F normalized, meaning what? Meaning that the normalizer of this subgroup is maximal among the normalizers of subgroups that are F conjugated with Q. So the cardinality of it is maximal, and I see that I need another notation here. If F phi is in F and Q is phi of P, then we say that Q is F isomorphic to P, or that Q belongs to the F isomorphism class of P, right? So just to and we can write that because you have here this isomorphism that is inside of the fusion system. So you only work with injective group homomorphism. So what does it mean in the situation here? In the situation here, Q fully F normalized, in fact, happens if and only if its normalizer in S is a CeLO B subgroup of the normalizer in G of this one. Okay, so just to see what is the case here. So when you have this situation, then phi from any morphism in the fusion system from P to Q extends to some morphism above where this n phi is nothing but the full preimage of the conjugations that you can see when you intersect them on the other side. So let me just write, so we are on the P side. So you just take the automorphisms given by S on P, send them by conjugation on the other side inside of the automorphism of Q, intersect them with the automorphisms in S of Q. This is a subgroup. You send it back. So you get a group of automorphisms of P, and you take the group inside of S, and you take the group that is generating this one. So mainly, just think of the fact that yes, I wanted to say here that Q is phi of P. Yes, you are completely right. Yeah, this is so the idea is that this morphism going into special subgroups, like those fully F normalized, extend to the maximal group to which it can extend. So you mainly, if it extends to something, then this group will have the property that is contained in this intersection. But you put the condition that you extend to the full maximality of those things. So just think that those two conditions catch somehow the CeLO theorems that are on the other side. So, for instance, just to give you an example, now that we are in this situation of saturation condition, then not too many cases can appear when you look at the saturated fusion system of on a given P group. So take for instance, example, there are so n phi is a subgroup of the normalizer in S of P. So you start with the automorphisms induced by the normalizer of P, right? The automorphisms on P. You send them, when you conjugate by phi, you send them on the automorphisms of Q. There, they can intersect the automorphisms in S of Q, which are, in fact, I didn't say that, but one can, once you have those two axioms, you can show that this is an CeLO P subgroup. But in this condition, I will just write here, I didn't want to charge you too much, but this is a CeLO P subgroup of the automorphisms in F of Q. Okay, so you send this inside of the automorphisms in F of Q. You look what's the intersection, then you transport it back. You will get back inside the automorphisms in S of P, and you take the full preimage with respect to the quotient by the normalizer. Okay? You can get the full normalizer, or you can get much less. Yeah, for sure you'll get the inner. So you get at least P inside P and times its centralizer. So this one contains at least P times its centralizer in S. Okay. Yeah, it's the largest. If you ever can extend, then this subgroup will be inside of this. So let's take an R, then R over CSP would be a subgroup of this thing. So this is the biggest to which you can extend. Okay. So there are three fusion system saturated fusion systems. On the dihedral group of order 8. If you don't know what it is, then it will be described in a second. So either the trivial one, you just look at the inner conjugations, or so this is where I hope the 8 will be defined if you didn't have it defined before. So it's the CeLO 2 subgroup of the symmetric 4 group, or you look at the general linear group over the field of F2 elements, 3 by 3 matrices. And so those are all the saturated fusion systems. And see the condition that we put, sorry? Up to isomorphism, yeah. There are those morphisms inside. Okay. Now you see that we insisted from the fact that the fusion system can come from a finite group. So we say that F is realizable. So isomorphism of fusion systems would be a group homomorphisms between the silos, between the p groups on which the fusion system is defined, that preserve the fusion, that sends the fusion on the. So in a sense, you can say that you have the same p group on which you build the fusion system. So you already have isomorphic S and S prime, let's say, and then this will send subgroups of the one and subgroups of the other. Yeah. This is the isomorphism that. So maybe something that I didn't say is that when you speak of saturated fusion system, so this notion was introduced by Puch in the 1990, already in some handwritten notes that appear much later, around 2005, I think, in Journal of Algebra. But so we say that F is realizable if there exists G finite group with S a silo P subgroup of G, such that F is the fusion system on S given by conjugation by elements of G. So otherwise, meaning that if you cannot realize, we say that look, I'm speaking here of F saturated. Okay. Otherwise, we say that F is exotic. And as a remark, and an important one, is that there are exotic fusion systems. And the first example, for instance, if you for p equals 2 was given by Ron Solomon already in the 1975, somehow historically speaking, because you see the fusion system were not there. But while doing his proof, this is what he managed to prove. And then the first examples for P odd, I think this was in 2005. So this is P equals 2, P the other half of the primes. And there are for P so this is here an S is 2 to the 10, and here the examples that they made was on 7 to the 3rd. This one is too big. Those one are extra special of order 7. So this is yeah. So it's sorry. Yeah. So what I wanted to say that is for P equals 2, there are just those families that were discovered at the time, and for P odd there are multiple examples that were like Brotto and Müller discovered some, Oliver and yes, and his co-authors, Ventura and yeah, I have a blank. Some in BLO2, and I said Brotto and Müller are others. Then Diaz Ruiz Virel completed the classification of some fusion system for P odd. Caspar Anderson, sorry. Thank you. Sorry. So for all. Yeah, this is so no. In the examples that they looked at extra special P group of order P to the cube. Among those, so only the reals will be real. Yeah, exactly. Yeah. No. Not not the extra special. Yeah, there are no other, because for P to the third you have two possible non-abelian P groups. Either it's extra special, either is the other one, the metacyclic one. And non-metacyclic, you know, that is resistant, so it's no. And only the extra specials could possibly give exotic fusion systems. The other thing that I wanted to say is that there is a way to be sure that your fusion system is realizable. So if F is constrained, meaning that there exists a centric F-centric subgroup. What does it mean for F-centric? So the center of all the conjugates, F conjugates of Q, is equal to the centralizer in S for all Q prime in the F conjugacy class of Q. So there exists F-centric such that F is in fact the normalizer in F. I will not really explain what this is. It's just this fusion system is, if you want, the normalizer fusion system of a fully normalized subgroup is all the morphisms that can be obtained as, if you want, restriction and extension of automorphisms of Q. I will not go too much into that, but just to say that if F has such a F-centric subgroup that is normal, then F is realizable. Even that we spoke now of this is the result of BCG LO, which goes by Brotto, Castellana, Grodal, Levy, and Oliver. So what about, so can the fusion in F be, say, controlled by less morphisms? You see already that when centric subgroups have special properties that one can catch all the fusion just by looking at somehow automorphisms of Q, then here the answer is yes. Alperin fusion theorem in his fusion system setting, this was 1967, says that F can be reconstructed by composition and restriction from the automorphisms of F-centric subgroup. Okay. so mainly you only need to know the automorphisms of those group, then you get the whole diffusion. Just to so just a notation, we'll denote by FC the full subcategory of F with or on F-centric subgroups of S. Okay, and in a sense, if you want, is that what this Alperin fusion theorem tells you is that FC determines F. The other way around is clear because FC is determined. Just to understand a little bit what are those F-centric subgroups, I'll just tell you that S is always F-centric. The trivial group is never F-centric if S is not trivial. And if you have a P group P that has a subgroup that is already F-centric, then P is itself F-centric. So if you want, the set of F-centric subgroup is closed by overgroups. Okay, so just to have an idea of what are those things. So now, what else determines the fusion? In a fusion system, in let's say the fusion in a finite group G. So the fusion in G determines for instance, it determines the homotopy type of the P completion of the classifying space of G. So this is the Martino Preedy conjecture. I think it appeared as a conjecture in 1995. It's at the time, I think they thought it was a theorem, and then that says that if so, let's say that G1, G2 are finite groups, and Si is Sylow P subgroup of Gi, then if you look at the fusion systems given by G1 and G2 on S1 respectively S2, then they are isomorphic if and only if the P-completed classifying space of BG1 is homotopy equivalent to the P-completed classifying space of BG2. What is the P-completion? Just in a nutshell, we say that, just to say that, so XY spaces, then the mod P cohomology of X is isomorphic to the mod P cohomology of Y if and only if the P completed spaces X and Y, the P completions are like the map inducing, yes, cohomology between the X and Y, yeah. Yeah, there's a z in between x and y. Always. Now, this doesn't tell us that the p completion of a space captures the mod p cohomology, but if x is p good, meaning that, for instance, not meaning that, for instance, if x is the classifying space of a finite group, this is our case, then, in fact, the mod p homology of x is the same as the one of the p completion. And this comes, in fact, from the fact that in this case, when x is p good, then x is homotopy equivalent. So I think it's a bit difficult to explain that more here. I just want to say that this is really a completion in those cases, like meaning that if you p complete twice, then you get back the p completion, and this is not, if you want, this is not the case if you, once your p completion is not homotopy equivalent, then you'll get a tower of p completed stuff that are not homotopy equivalent. So. Like, sorry, if x and y, yeah. I thought that this was true for all spaces, but I thought I read that in your, like this one. I think this one is. So yeah, you need a map from x to y. Okay. So anyway, the hard part. Well, both are hard part in this thing, but somehow I will not explain. I thought I'll have the time, but I will not have the time to explain more about that. This is, let's say, more classical, okay, by a theorem of Mislin, and also Martino-Pridi. Using a theorem of Mislin and then proven, by Martino-Pridi. The other way around was finished by Bob in a sequence of 2 papers, 2004, 2006, and he, for that, needed the centric linking system. Associated to a fusion system. So what is this for G? If you want. Yeah, I wanted to say that afterward. Once I give the what is the, so for G a group, what is LC S of G? So it's a category objects are the subgroups of S that are F centric, sorry, with respect to the fusion in G centric. Just to make a comment, this means that it's equivalent to ask that the that the center of Q is a CeLO P subgroup of the centralizer. You see, once you have G, explaining things are sometimes more direct. But once you have the fusion system, you see what you have to prove. So, as homomorphisms, you just take the transporter from P to Q, and you quotient out, instead of quotienting all the morphisms that are trivial, all the conjugation, all the elements giving trivial conjugation, you just quotient out the P prime part of it, in a sense that in this situation, it's easy to see that the centralizer in G of P is nothing but, so it's isomorphic to the center of Q cross of P, because it's P here, you're right. It's a Q there, yes. Cross direct product with some P prime part of that. Okay, so this is the centric linking system associated with G. And the thing that relates the centric linking system with our Martino-Pridy conjecture is that BLO, so Brotto, Levy, and Oliver, did I say it already? But everybody knows what BLO means. In 2003, in fact, the paper was already ready in 2000, but took to be published took some time. So BLO showed that if you take the nerve of this category and you P completed, then you get something that's homotopy equivalent to the P completion of the classifying space of G. Okay. So in a sense, you see that one needs a little bit more. One needs a general definition for a fusion system of a centric linking system, and show that there is always a unique centric linking system in the situation when the fusion system comes from a finite group. So just to have that. So now in general, for a saturated fusion system, F, let's define the centric linking system. So LC, it will be a category that will contain the transporter fusion system on centric things, and will project on, let's say in a second, what are so the objects will be the same for everybody. So objects here are just subgroups of the CeLO that are F-centric. For the homes, here we have just the transporter from S from P to Q by S. Then let's just keep it, because we are about to define it, so just leave it as morphisms. And then here are the morphisms in our fusion system. Some people don't write that as home from L because they say those are not group homomorphisms. So those are something that's above group homomorphisms. So if you call this delta PQ and this the projection PQ, that you have some natural natural requirements for those maps to satisfy, just to stick with the definition in the general case. So first of all, so P will act freely on the morphisms in L from P to Q, and so this is just the orbit map. Then something that is natural is that when you take somebody here, yes, you're totally right. I got too quickly. Yes, want to model by the center. Then when you take an element in here, you look what's as morphism inside of L, and then apply the projection. Then you really get a morphism from P to Q. Then you want this to be the conjugation by U. And finally, you want some diagram to commute. So if you take U in P and psi, a morphism in LC from in the centric linking system from P to Q, then doing the morphism given by U between P, or the one given by now you want to apply something to U, but you cannot apply morphism in L to U because they don't know what it means. You have first to transform it in a morphism of Q. Then you can apply it. So a morphism in the fusion system, then apply it to U. Get an element in the normalizer of Q and apply phi Q. Okay, and you want that to commute in L. Right. Just see so fusion centric linking systems are trying to capture now the P completion of the classifying spaces of a group that doesn't exist. So it's in fact it will be. So if you want the taking the nerve of this, no, so it's the classifying space. Be completed of the data S fusion system and centric linking system. Right. Okay. Anyway, now coming back to what Bob Oliver showed, 2004, 2006. So he showed that there exists is a unique centric linking system associated to the fusion system of a group. Okay, so I recall you that here we speak of finite. Finite. So there exists a unique centric linking system, and this one is the one, or it's isomorphic to the one that you expect, right? The one that you already constructed. And this uses the classification of finite simple groups. Then later, Cermak in 2011 showed that for any saturated fusion system, F on S, there exists a unique centric linking system associated to F, and very recently Glauberman and Lind 2015, if I remember well. So this was also using classification of finite simple group. So that's a no need for the whole classification of finite simple groups. One can get it directly without using that. Okay, so this is where the story is now with respect to the centric linking systems. And so the fact that Bob showed that there is a unique centric linking system associated to a fusion system of a group, this was the main ingredient to show the other way of Martino-Pridy conjecture. That's here. Not even erase it. And I, just for the last 5 minutes, I promised that I will take care of that, but I'm not sure I'll have the time. I wanted just to give a hint on double Burnside module and ring. That's also very tightly related to the fusion system. Hopefully I managed to give that. So when G and H are groups, GH biset, you can see it as a G cross H set just by looking at, so biset means that the action is on both sides, but this is the same as looking at the action in front. You have to change from left to right action, so change H in H minus 1 X. And so a GH would be the Grothendieck group of, we'll take it topologist way of left free GH bisets. So for the disjoint union, meaning that the group law in here is just making the disjoint union. And if you take such Grothendieck group, there's one that is a lot used when you work with fusion systems. So it would be the Grothendieck group of bi-free. So you want the action of left and right GH biset. Okay, so it's just a subgroup of this one. Then you have some external multiplication. Oh, A GH cross A HK into A GK is just taking a biset, a GH biset here, a HK biset here, and making their product, if you want, direct product over H, meaning that you just take the direct product and you quotient out the action of H. Okay, and this makes, so this multiplication will make A SS in a ring, the double Burnside ring. Now, just for if I can take 5 more minutes. So here wait a second, just okay. So there's a basis for the left free bimodule, double Burnside module. Those quotients of the so G cross H has a natural GH biset structure, but you want to quotient out all the graph of this morphism. So the phi of x x or x in k, where phi is a morphism from k into G, and k is a subgroup of H. Okay, so those are, this gives the, because of the freeness, we can represent all the, so this is up to GH conjugacy, but we can represent all the all the transitive biset by such morphisms, and for a basis for a free GH would be the same with phi injective. Okay, and I just wanted to tell you what F stability is. Okay, so like in a group, when X is a G set, what do you have? For P, a subgroup of G, when you look at X and you restrict it to P, or you restrict it to P via some conjugation, meaning that here U in P acts normally, or here acts once I conjugate it by G, then those are isomorphic as P sets. Then we'll say that X, a S set, is F stable if we have exactly the same for all P subgroup of Q and phi fusion inside of the fusion system, X restricted to P, or X restricted to P via phi again. So here the U in P acts normally, here acts once I apply phi to it. Okay, those are isomorphic as P sets. And we say that X and S biset is F stable if the same thing happens but left and right. So X is left and right F stable. Let me just introduce what, just to see what are glance of the results here. Biset would be characteristic for a fusion system. So X, A, S is characteristic for a fusion system F if we have different things. First, X is F generated, meaning that is constructed by all the fusions. Sorry, I should give that. 2, X is F stable. And 3, we want the augmentation, which is given that anyway you have a free action on one side, this is an integer, we want this to be prime to P. Okay. And so characteristic. So where I wanted to get is that BLO in the same great paper of 2003 managed to construct, there exist for any F saturated, there exist omega characteristic for F. But this is not necessary, not unique. Later, Ragnarsson in 2006 says that for all F saturated, there exists a unique element in the Grothendieck, in the Burnside ring, where we allow local coefficients. that is, I didn't explain what this is, but that is symmetric. We'll see maybe the next days. And omega f characteristic idempotent. And I will just finish. Yeah, I'll finish with one thing that the other way around, if there exist. So, Puch and Gary and myself, let's say 2009. If there exist a characteristic, so if there exists omega, let's say characteristic for f, even without considering saturation, then f is saturated. So just to say that on one side, the fusion systems, and on the other side, this double Burnside ring are related. One can read information from one side into the other, and vice versa. Okay, thank you, and sorry for